The dream of a galactic club, a thriving interstellar society where advanced civilizations exchange knowledge across the stars, has long been a foundation of science fiction. It is a powerful image, countless worlds, connected by shared discovery, trading ideas through the vastness of space. But when we examine reality through the framework of higher dimensional physics, we are forced to confront a far more sobering conclusion. Theoretical models increasingly suggest that our isolation may not be accidental. We may not simply be alone by chance. Instead, we may be cosmically quarantined by the very laws that govern space-time itself. The universe, in all its scale and age, appears to have constructed barriers that are not technological but fundamental. These are not walls built of matter. They are walls built of distance, velocity, and time. And no matter how advanced a civilization becomes, those limits remain embedded in the structure of reality. If we evaluate our status using the Kaku scale of technological development, humanity is approaching what could be described as a Type I civilization. Yet, even at this early stage, we remain confined to a local region that is effectively empty. Consider our nearest stellar neighbor, Proxima Centauri, located 4.24 light-years away. In astronomical language, that distance sounds small, but when we measure it against our real capabilities, the scale becomes overwhelming. The fastest object humanity has ever built, the Parker Solar Probe, reached a speed of approximately 430,000 miles per hour. That achievement represents the peak of our engineering precision, yet at that velocity, a journey to Proxima Centauri would require more than 6,000 years. That is longer than the entire span of recorded human history simply to reach the nearest star. This is the first barrier, the immense scale of space itself. In our region of the Milky Way, the average distance between stars is roughly 5 light-years. The galaxy is not a dense city filled with neighboring systems packed closely together. It resembles an archipelago, small islands of matter separated by enormous stretches of darkness. Even light, the fastest entity in the universe, takes years to cross these separations. For any species, operating within the standard model of physics, this distance transforms interstellar contact from difficult into practically unreachable. Some may argue that a sufficiently advanced civilization could simply travel faster. That assumption leads directly to the second and more absolute barrier, the universal speed limit. In 1905, Einstein's theory of special relativity established that the speed of light, exactly 299,792,458 meters per second, is not a flexible threshold. It is a fixed property of spacetime. As an object with mass accelerates toward that limit, its effective mass increases. The energy required to continue accelerating rises exponentially. To actually reach the speed of light would require infinite energy. In a finite universe, infinite energy does not exist. Even the solutions that appear promising in mathematics begin to collapse under physical scrutiny. Concepts such as warp drives and wormholes suggest shortcuts through spacetime. The Alcubierre drive, for example, proposes compressing spacetime ahead of a vessel and expanding it behind. Yet the equations require forms of negative mass or exotic energy densities that have never been observed in stable form. Stabilizing even a microscopic wormhole would demand energy comparable to converting multiple planets entirely into pure energy. The scale of this requirement is not merely extreme, it is fundamentally incompatible with our current understanding of matter and thermodynamics. At this point, the pattern becomes clear. The obstacle is not imagination, it is structure. The universe does not merely make interstellar travel difficult, it makes it functionally impossible under known physics. And this realization marks only the beginning of a deeper examination into why the cosmos may be designed for observation, but not for contact. Even if we set aside warp drives and wormholes and imagine a civilization capable of reaching just 10% of the speed of light, the challenge remains overwhelming. 10% may sound modest compared to light speed, but in physical terms, it is staggering. To accelerate a spacecraft weighing around 1,000 tons, roughly comparable to 2 international space stations, to 10% of light speed would require an energy release equivalent to detonating approximately 150,000 nuclear weapons. This is not a routine engineering obstacle. It represents an energy demand on a planetary scale. And acceleration is only the first step. Once the ship reaches that velocity, space itself becomes hostile in a new way. The interstellar medium is not a perfect vacuum. It contains sparse hydrogen atoms and microscopic dust particles. At everyday speeds, these particles are harmless, but at relativistic velocity, even a single hydrogen atom carries the kinetic energy of a high-speed bullet. A spacecraft traveling at 10% of light speed would collide with trillions of such particles every second. Instead of smoothly crossing empty space, it would endure constant high-energy impacts. To survive this environment, the ship would need meters of shielding, perhaps layers of water or dense metal, to absorb the impacts and radiation produced by these collisions. But shielding adds mass. Additional mass requires more fuel. More fuel increases mass again. This is the tyranny of the rocket equation, a mathematical trap that multiplies difficulty with every attempt to solve it. Each solution intensifies the problem it tries to fix. Suppose a civilization somehow solves both the energy and shielding challenges. There remains another consequence: time dilation. According to special relativity, a crew traveling at 99.9% of light speed might experience a journey lasting 10 years. Meanwhile, more than 2 centuries would pass on Earth. Upon return, if return were possible, the society that launched them would be drastically transformed. Languages would evolve. Political systems would change. Generations would rise and fall. Every interstellar mission becomes a one-way trip into the future. This temporal separation makes the idea of a unified interstellar empire unrealistic. Even a Type II civilization capable of harnessing the energy output of an entire star would face communication delays measured in decades or centuries. Colonies would not remain culturally synchronized. They would diverge, becoming isolated branches of a once unified species. From a gravitational perspective, large-scale interstellar travel would also leave detectable signatures. The energy required to accelerate and decelerate massive vessels should produce measurable gravitational waves. Observatories like LIGO and Virgo detect distortions in spacetime from colliding black holes billions of light-years away. Yet we observe no gravitational disturbances within our galaxy that suggest engineered interstellar travel. The silence remains consistent with the presence of a barrier. Through this lens, the Fermi paradox appears less mysterious. It may not be that intelligent life is absent. It may be that it is confined. Civilizations could emerge and vanish within 100,000 years, an instant in cosmic history. The probability of 2 technological societies overlapping in both time and reachable space becomes extremely small. The universe may not be structured for communication. It may be structured for separation. Timing may be as restrictive as distance. Even if intelligent life arises frequently across the galaxy, technological phases may be brief. A civilization might develop advanced communication within a few thousand years. Yet the same capabilities that enable growth can also produce self-destruction. Environmental collapse, uncontrolled artificial intelligence, engineered biological threats, or internal conflict could sharply limit the lifespan of advanced societies. In a universe that is 13.8 billion years old, a technological window lasting only a few thousand years is almost invisible. For two civilizations to establish contact, they must exist within close spatial proximity and within the same narrow time frame. The probability of both conditions aligning is extremely low. Civilizations may flicker like brief signals in a vast and ancient system, rarely overlapping. Compounding this difficulty is the expansion of the universe itself. Dark energy, which constitutes roughly 68% of the total mass energy of the cosmos, is accelerating the separation between distant galaxies. Over immense timescales, galaxies outside our local group will recede beyond the cosmic horizon. Their light will stretch into longer wavelengths, shifting from visible to infrared and eventually beyond detectability. This creates a permanent boundary. Beyond the cosmic horizon, no signal, regardless of strength, can ever reach us. Even a highly advanced Type 3 civilization capable of harnessing the energy of an entire galaxy would eventually confront a shrinking observable universe. In the far future, the night sky may appear nearly empty, with only local gravitationally bound structures remaining visible. We may currently exist in a rare observational era. The universe is old enough for life to have formed, yet young enough that distant galaxies remain visible. But observation does not equal interaction. When we detect exoplanets within habitable zones, we are observing light that left those systems years or centuries ago. We are seeing their past, not their present. Some theoretical perspectives deepen this isolation further. If our three-dimensional universe is a projection of information encoded on a distant boundary, as suggested by certain holographic principles, then the speed of light could function as an informational limit. Just as a simulation has maximum rendering boundaries to maintain stability, the universe may enforce a maximum interaction radius to preserve causality. Across relativity, cosmology, and quantum theory, the conclusion converges. The barriers are structural. They are not waiting for better engines. They are features of reality itself. Beyond physical distance and cosmic expansion lies another constraint, the preservation of causality. The chronology protection conjecture proposes that the laws of physics prevent paradoxes that would disrupt cause and effect. Faster-than-light travel, if realized in practical form, could allow information or matter to move backward in time under certain reference frames. Such violations would destabilize the coherent structure of events. While mathematical solutions for warp drives and wormholes can exist within equations, implementing them introduces instabilities. Exotic energy requirements, quantum fluctuations, and infinite stress energy tensors emerge in the calculations. Reality appears to tolerate these solutions on paper, but resists their physical realization. This resistance may not be accidental. A universe where civilizations could easily traverse galaxies might also be prone to large-scale instability. Rapid expansion across star systems could produce resource conflicts or uncontrollable technological escalation. By imposing vast separations, the laws of physics may enforce independent development. On Earth, we often imagine contact with advanced civilizations as salvation or validation, yet the structure of space-time suggests that no external intervention is coming. The responsibility for survival and progress rests entirely within our own planetary boundaries. Consider Voyager 1 and Voyager 2. They have entered interstellar space, carrying records of human culture. Yet even traveling at tens of thousands of miles per hour, they will require tens of thousands of years to approach another star system. Long before then, their power systems will fail. Micrometeoroids will erode their surfaces. The civilization that launched them may change beyond recognition. These probes symbolize curiosity, but they also highlight limitation. The relativistic firewall does not merely slow expansion, it defines scale. We can explore our solar system extensively, we may colonize nearby planets. But interstellar civilization, under current physical laws, remains beyond practical reach. Constants such as the fine structure constant and gravitational constant allow stable atoms and life-supporting chemistry. Yet those same constants also restrict movement across cosmic distances. Under different parameters, the galaxy might feel smaller. In this universe, under these laws, it does not. Isolation emerges not as failure, but as structure. The accelerating expansion of space introduces a final large-scale boundary. Dark energy stretches space-time continuously, increasing the separation between gravitationally unbound regions. Our local group remains intact due to gravity, but distant clusters recede ever faster. Over trillions of years, galaxies beyond our local cluster will move past the cosmic horizon. Their light will redshift beyond detectability. Future civilizations within our galaxy may not even know that other galaxies once existed. They will see only their local stars against a dark background. This suggests we are living in a temporary era of visibility. The cosmic environment currently allows observation of distant structures. Yet this window will not remain open indefinitely. Expansion ensures increasing isolation over time. If a Type 3 civilization emerged, harnessing the energy of an entire galaxy, it would still face this horizon. Expansion itself would limit long-term interaction across clusters. No signal could overcome space-time stretching beyond a certain threshold. Some theoretical models propose that our universe may operate under holographic principles where information is encoded on a distant boundary surface. If so, limits like the speed of light and cosmic horizons may represent informational constraints rather than mechanical ones. They maintain coherence within the system. When viewed collectively, distance, relativistic limits, energy constraints, interstellar hazards, temporal discontinuity, cosmic expansion, and causal protection, the conclusion becomes consistent. The universe permits observation. It restricts interaction. Through this comprehensive lens, the Fermi paradox shifts from mystery to geometry. It may not be that life is rare, it may be that life is separated by design. Civilizations may arise across the galaxy, each developing science, culture, and technology. Yet they remain confined within their local regions, unable to bridge the immense gaps imposed by space-time. We observe ancient starlight, but we are seeing history. We detect planets in habitable zones, but we are viewing past conditions. Any signal we transmit to a star 1,000 light-years away would require 1,000 years to arrive and another 1,000 years for a response. By then, both civilizations could have transformed or vanished. The universe appears magnificent and rich with possibility, yet structured for solitude. The relativistic firewall remains intact. The cosmic horizon continues to expand. Causality remains protected. Each island of consciousness stands alone, separated not by choice, but by geometry. This realization is not defeat, it is responsibility. If no interstellar civilization can easily reach us, then no external force will solve our challenges. The survival and advancement of our species depend entirely on decisions made here. We can continue exploring, studying, and pushing boundaries within our solar system. We can deepen our understanding of physics and refine our technologies, but we must also accept the framework within which we operate. The universe may contain countless civilizations, yet the gulf between here and there remains unbridged. We are part of a vast design, but within it we stand solitary. If this perspective reshapes how you see our place in the cosmos. Continue exploring these ideas with us. Subscribe, stay engaged, and join the conversation as we examine the limits and possibilities of our universe.